Okay, well, welcome back to the stirring conclusion of section 4.2. The last video ended rather abruptly when I realized that we actually have two different formulas for the time to peak. My formula that I derived did not match the formula in the book. So what I want to do now is investigate which of these is correct, so that you know which one to use if you ever need to calculate the time to peak. So which time to peak formula is correct? And just a reminder or a summary at this point, the book gives you the formula. The time to peak when your stock level is at a level m is t equal to the log of c over m minus 1 divided by the log of 1 plus r. And the formula that I found starts out similar. It says that the time to peak is t equal to the natural log of c over m minus 1, so that part is pretty close at least. But instead of an log of 1 plus r in the bottom, it's just an r. So which of these is correct? Well, to do this, let's actually build a logistic model and check this. So let's set a logistic model. Like I mentioned, one of the cases where it's easy to build a logistic model and the logistic model is fairly accurate is the spread of a disease. So let's look at the spread of a disease in a town of 10,000. And we are going to ignore the impact of immunity on this. Which, depending upon the disease, can make quite a big difference. The reason we're going to ignore immunity and say that everyone in the population is actually going to be susceptible to this disease is because I want to use that 10,000 as my carrying capacity. That just makes it easy to say what the carrying capacity should be. At the end of the spread of the disease, all 10,000 people should have gotten sick at some point. Whereas if we don't neglect immunity, right, some percentage of the population isn't ever going to get infected and will be outside of our model, so we won't really know what the carrying capacity is. Okay, so making that assumption, let's say that 200 people are infected. When the outbreak is discovered. And that 1 month later, 1,000 people have been infected. And for the logistic model for the spread of a disease, when we say infected, these are the people who have ever had the disease. So some of these people may have recovered already, but over the course of the disease, we're saying that in the first month, there were 1,000 people impacted. Okay, so I mentioned the reason we're going to ignore immunity is so we can say the carrying capacity is 10,000. This information also gives us the initial stock value. It says S sub 0 is 200, so when we first realized there's an infection and we start taking data, the first stock level of infected people will be 200. Because we're given a measurement in 1 month, we'll say that our time t is being measured in 1 month. And if we're measuring time in months and we say after 1 month 1,000 people have been infected, in symbols the way we would write that is we'd say S of 1 is 1,000. Okay, so let's set up our model. Remember, the general formula for a model is that S of t is the carrying capacity divided by 1 plus c minus s sub 0 divided by s sub 0 times e to the negative rt. And let's plug in what we know. The carrying capacity is going to be 10,000. This 1. And we know the carrying capacity in the initial value, so let me do some scratch work over here to figure out what this number is going to be. C minus the initial value is going to be 10,000 minus 200. That gives us 9,800. And S sub 0 is 200. All those zeros cancel, so I get 98 over 2. And that simplifies to 49. So this coefficient here is just going to be the number 49, e to the negative rt. And we're missing the r value. So let's use the extra piece of information that we have to solve for it. So we're going to use the fact that S of 1 is 1,000 to solve for r. Okay. And so S sub 1, if I look at my formula for S of t, which is here, and plug in t equal to 1, I get 10,000 divided by 1 plus 49 e to the negative r times t, so e to the negative r times 1. And I'm told that that's 1,000. So I'm going to solve for the r that makes these two things equal. I can divide both sides by 1,000. And that gives me 10 over this fraction is equal to 1, so I'll multiply both sides by this, and I get 10 is equal to 1 plus 49 e to the negative r. Subtract 1 to get 9 is equal to 49 e to the negative r. And so 9 over 49 is e to the negative r. To get r out of the exponent, take the natural log. The natural log of 9 over 49 is negative r, and multiply both sides by r. I'm also going to switch sides, so, multiply both sides by negative 1, and I'm going to switch the sides so that r is over here on the left. I get r is equal to negative ln of 9 over 49. And you can plug that into your calculator. You get that that's about 1.7. It's a little less than 1.7. Okay, so there's our r value, which means that our model for the spread of this disease is S of t is equal to 10,000 divided by 1 plus 49 e to the negative r times t. Okay, and we want to use this model to check the two formulas we have for the time to peak. So let's use that data that we have using a value of n equal to 1,000, which corresponds to t equal to 1, since we are told that after 1 month, 1,000 people are infected. Let's answer the question, what is the time to peak? Okay, and let's look at what the two formulas predict. The book's formula says that the time to peak is the log of c over m minus 1 divided by the log of 1 plus r. Well, if you plug in all of our information, that's the log. C is 10,000, so divided by m gets you 10, and when you subtract 1, that gives you a 9. Divided by the log of 1 plus r, which we just solved for. R was 1.7, so the log of 2.7. And again, you can plug that into a calculator, and this tells you that the time to peak should be 2.2 months. So there's one potential answer. If we use my formula instead, then the time to peak should be the natural log of c over m minus 1, just divided by r. That comes out to the natural log of 9 divided by 1.7, and that's approximately 1.3 months. So the question is, which one's right? Well, to answer that, let's not use either formula and calculate when the peak time occurs and see which answer we get. So when does the peak happen? Well, we know the peak happens when the stock level, or the number of infected people, is half of the carrying capacity. So when S of t is c over 2, the carrying capacity for this example is the total population, which is 10,000. So when I divide by 2, I get 5,000. And I want to know what t value makes that happen. So let's go back to our model. S of t is 10,000 divided by 1 plus 49 e to the negative 1.7 t, and I want to know when is that equal to 5,000. Okay, well, let's divide everything by 5,000, because I've got that as a factor on both sides. I get 2 over 1 plus 49 e to the negative 1.7 t is equal to 1. Multiply both sides by this denominator. 2 is equal to 1 plus 49 e to the negative 1.7 t. Subtract 1. Divide by 49. To get t out of the exponent, take the natural log of everything. And solve for t by dividing by this negative 1.7. So I get that the peak flow happens when t is equal to the ln of 1 over 49 divided by negative 1.7, which is approximately 2.3 months. So I know when the peak is going to happen. I was looking at the time to peak from 1 month. So the time to peak Well, if I'm at 1 month and I know the peak is going to happen at 2.3 months, then the time between those two is the difference, which is 1.3 months. Okay, so let's go back up to the formula and see if either of them predicted that the time to peak should be 1.3 months. Okay, and the one that predicted 1.3 months was the formula we derived, or I derived in the last video. And that ends up being the correct formula. So I honestly don't know where the book is getting this formula. Clearly some pieces are right. I don't know where that came from. Maybe it's just a typo. But let me give you the correct formula then. So the correct formula for time to peak if you're at a stock level m is that the time it will take for you to get to the peak is the natural log of c over m minus 1 divided by r. So if you are answering a question about time to peak, make sure that you use this correct formula instead of the one in the book. And this might seem like a weird exercise, who really cares, but this is an important question right now because, and this example sort of brings it home. But if we're studying the rate of an infection, one of the things that you would be interested in is the number of new cases and being able to predict when the number of new cases is going to peak. Because if you know when it's going to peak and you know what it's going to peak at, then you know what your capacity in the hospitals has to be. So this is not just an intellectual exercise right now. This has real-world impacts that people are working really hard to get a good logistic model so that they can make a good prediction for. And hopefully they're using the correct formula for the time to peak. I'm sure they are. Okay, so there's the correct answer. We'll be moving on now. We're done with 4.2. We'll be moving on to a different chapter in the book where we'll study a little bit of statistics and what we can say when we have large data sets to draw from. So something entirely different, which I think will be a nice change of pace.